Now that Griselda has taught us a little bit about the theory, let's dive into the assumptions.
A quick disclaimer. The model that we created was for demonstration purposes only. Not all of our assumptions will be met, but we want to give you the code so that you can check future assumptions of future models.
Here we go. In this video, I will brief all of you on the assumptions of multiple linear regression with interaction while simultaneously demonstrating on how to check them using R. Let's get started with the assumptions. The assumptions are as follows. First, linearity. Here, we check for a linear relationship between the outcome variable and the independent variables. Second, multivariate normality. This assumption checks for the normality of the error terms. Third, independence. Here we check for multicollinearity of the data. Fourth, homoscedasticity, which is also known as the test of equal variances. And lastly, autocorrelation, which checks for the independence of the error terms. Let's begin by breaking down these assumptions one by one, starting with linearity. Here, we want to see a linear relationship between the outcome variables and the independent variables. This can very easily be understood by looking at a scatter plot of the data. I will be showing the scatter plot by running this particular code in R. As you can see from our scatter plot, there is a missing linear relationship between the independent variables and the dependent variables. Next is multivariate normality. We want to see if the residuals are normally distributed. We can check for normality by visualizing a QQ plot. The points should lie close to the line to be considered to be normally distributed. It should not appear to be skewed. I will run this code for the QQ plot. As you can see from the QQ plot, some of our points do not appear close to the line, which means there are some issues with normality. We can also test for normality with the Shapiro-Wilk test. The null hypothesis for this test is that the data is normal. So a small p-value would indicate that the data is not normal. I will run this test and you can see very clearly that our p-value is very small, almost approximating to 0. Therefore, the data is not normal. Now, when the sample size is sufficiently large, like ours, that is greater than 200, the residuals will be approximately normal by the central limit theorem. Violations of normality tend to not contribute to bias or inefficiency in regression models. Thus, the only importantness for the calculation of p-values are for significance testing, but this is only a consideration when the sample size is very small. Moving on, we'll now talk about homoscedasticity. This assumption is concerned with the variation of residuals or the amount of error in the model. It states that the variance of the error term is analogous for each independent variable across the model. Alternatively, if the variances are not equal for the independent variables across the model, this would indicate a condition defined as heteroscedasticity. Now, if the data actually displays heteroscedasticity, it would mean that we have overestimated the goodness of fit, which basically tells us how consistent our variables are. The advantage of this particular assumption is that you can easily and very clearly point out if there is a breach, which helps us define the accuracy of the model. The following are the ways we can examine homoscedasticity. Let's start with the first one. Here we visualize a basic scatter plot that plots the residuals, that is the error of predictor variables, versus the predicted values. Homoscedasticity is indicated when the residuals are evenly scattered around the horizontal line that takes on a rectangular shape. This is the R code for a basic scatter plot. As you can see here, there is a clear pattern which represents a bow tie shape, which concludes that homoscedasticity is not present. Moving forward, we can use a statistical test known as the Bruish-Pagan test, which is a chi-square test. Here, the test statistic is distributed with k degrees of freedom. In R, the test is executed by the function NCV test, right here, that is available in the car package. For homoscedasticity to be present, the chi-square value has to be low and the p-value has to be less than 0.05. This gives us, as you can see from the output of the NCV test, it gives us a very high chi-square value and the p-value almost approximates to 0. Concluding from all of this, we can say that the assumption of homoscedasticity is clearly not met and the data follows heteroscedasticity. But there is always a way to rectify this. It would be that you reconstruct the model with a new predictor variable or more, or perform a variable transformation precisely using Box-Cox transformation. The fourth assumption tests the multicollinearity. Multiple linear regression assumes that there is no multicollinearity in the data. It occurs if the independent variables are too highly correlated with one another. We can check for multicollinearity with a correlation matrix or variance inflation factor known as the VIF scores. The VIF scores should be below 10. If the VIF scores are above 10, it would indicate correlation and is considered unacceptable. It is important to note that there is a controversy regarding how large a VIF score should be to cause issues. Some statisticians argue for a more conservative VIF score, arguing that it should not exceed 5. In general, the higher the VIF score, the less reliable is the relationship or the result of the regression model. I will test these scores by running this code. As you can see, the VIF scores for both our independent variables are less than 5, and this concludes that the multicollinearity assumption is met. Lastly, let's talk about autocorrelation. For testing the assumption of autocorrelation, we will use the statistical test known as the Durbin-Watson statistic. The Durbin-Watson statistic indicates whether there is autocorrelation and the degree at which it is present. Autocorrelation normally ranges between 0 and 4. The values that are less than 2 indicate positive autocorrelation, and the values greater than 2 indicate negative autocorrelation. For testing autocorrelation in R, we download the library lmtest and then run the test Durbin-Watson test. As you can see that our Durbin-Watson value is 1.483, which is not very close to 2, which concludes that we have a positive autocorrelation and our p-value is less than 0.5, whereas it should be greater than 0.5. And our alternative hypothesis is accepted, saying that there is autocorrelation and it is greater than 0. Therefore, this assumption also fails to be accepted.